All right. Thanks, everybody, for joining us again. Our next presenter is Mr. Mark Finney. Mr. Mark Finney is a senior science and research forester with the U.S. Forest Service Rocky Mountain Research Station, Missoula Fire Science Laboratory. He's worked at the Missoula Lab since 1993. He is the team lead for experimental research on physical processes and fire behavior. His wildfire modeling work includes FARSIGHT, FlameMap, and FSIM. He holds a PhD in wildland fire science from University of California at Berkeley, a Master's of Science in Fire Ecology from University of Washington, and a Bachelor of Science in Forestry from Colorado State University. So thank you so much for Mr. Finney for joining us. I will be giving a 5-minute warning getting towards the end of your presentation just to allow time for questions at the end. So, all right, I'll turn it over to you, Mr. Finney.
Okay, I'm trying to share the screen here. Doesn't seem to, oh, there we go. Okay, good. Okay, hello everyone. Glad to be here. Let's get right to it. Please let me know if you're not seeing the screen. So I'm talking about research on wildfire ignition by exploding targets. Well, how common are these kinds of ignitions? Well, from 1995 to 2018, about 2,226 fires are supposedly caused by these. Now, this is very difficult to determine because the cause categories that we have for the National Association of State Forests don't explicitly include a cause category for fire occurrence by firearms. The number of ignitions amount to 0.2%, so less than 1% of all ignitions were caused by firearms and exploding targets. So you can see here on the left, this is the cause category. It does not include firearms. The new cause standard, general cause, does include firearms and exploding targets. So of those 2,000 ignitions, 40% are caused by recreational use of firearms. About 5% are caused by exploding targets, 35% from shooting inert projectiles at an inert target, such as a steel plate or a dirt berm. So the number of fires that we see from firearm-related causes are going up, almost non-existent in 1995 to many dozens occurring in modern years. Most of these, about 4 times more ignitions by just shooting inert targets with modern rifles compared to exploding targets. Now, these occur mostly in the West. You can see the number of ignitions reported throughout the Western states and in Alaska, and this is because of the dry conditions. This is for exploding targets, although there's not as many. It's this very similar pattern. Okay, so let's talk about how these ignitions happen. I'm going to refer to 3 different studies. I've uploaded these studies to the site so that you can download them, but you can find them on the internet. Talk about muzzle-loading rifle ignitions, modern rifle bullets, and then exploding targets. So let's talk about muzzle-loading rifles to start with. The way these work is the charge, the powder charge, and the projectile are loaded from the muzzle. That's why it's called a muzzle loader. And if you look on the left, there's different kinds of projectiles. The upper left, different kind of projectiles that can be used. There are regular bullets, conical bullets without a patch, but the one on the right in that center or in that upper left picture is the one we explored the most. That's a patched round ball. It's a round ball with a cotton patch. Cotton patch can be lubricated. And when you ram the powder charge down the barrel along with the ball, the patch sits right on the powder charge. And what happens when the powder charge is ignited, when the person shooting squeezes the trigger and the hammer drops, this powder charge starts to burn very rapidly, and it envelops the patch and the ball in burning gases, which is then forced out the barrel. Now, the way we tested the ignitions here is we put a piece of craft paper down in our laboratory, and then we fired the rifle down this firing lane, hoping to catch pieces of the projectile and or the patch, and we shot into a bullet trap. Well, what we found was that on this craft paper, 12 times out of 105 rounds, we found smoldering patches. And someone doesn't have their mic muted. Smoldering patches, and these smoldering patches would burn holes in the paper. So 12 rounds out of 105 caused ignitions from the smoldering cotton patch. So here's the summary of this. Percussion and flintlocks are both kinds of rifles, use the same exact projectile with the cotton patch. We only saw this with a ball and cotton patch, not with just a regular conical lead projectile. Both lubricated and non-lubricated patches cause ignitions. These are smoldering ignitions, means they take a while before you would see a transition to flaming. So it may be hours even. This only occurs under very hot, dry weather conditions. Let's talk about modern rifle bullets. This is the center study here. We did this in 2013. And I have this picture here to contrast the way the modern rifle bullets work compared to the muzzle loader. So in a modern rifle cartridge, what you have is a projectile that is the bullet made of copper, lead, or steel components, and it's sitting within a case, a brass case usually, but sometimes a steel case. And the smokeless powder charge is then contained in the case. And there's many studies of bullet impacts from the military, as you can imagine. Militaries all over the world have studied ballistic impacts, but almost none of them have studied what is the temperature of the bullet or the condition of it after it impacts. And so what happens here is there's kinetic energy. The energy of motion is converted upon the bullet slowing down rapidly, converted into thermal energy. And this means the thermal energy is contained in these very hot fragments of the bullet. So let me explain this without the context of the ballistic impacts. This is just a wire. If you've ever bent a wire until it's broken, you notice that where it's bent, it gets hot. And so this is a thermal image, thermal video of us bending a wire between two vice grips. And you can see where the wire is fatiguing, you're breaking metal crystals there, that it gets very warm. And imagine this happening when a bullet smacks either a rock or a steel plate. In a fraction of a second of motion is transferred into thermal energy. Okay, so we built a bullet trap in order to capture these fragments. It's composed of a deflection plate where the bullet impacts that, it fragments, the fragments drop down into a catch box or a collection box, and they bounce around in there. This is a picture of the actual apparatus. It's a 3/4 inch steel plate made of AR-500 steel. It's a work hardening steel, so it doesn't dent very much upon ballistic impact. And then there's the collector box. Inside that collector box is filled with peat, very dry peat, which is just like duff or litter out in the wildlands, but it's very controllable this way. And we can adjust the angle of this deflector plate, which is important because it changes the amount of fragments that you get. If you have an oblique impact, you have much larger fragments than you would if you have a very flat impact. Okay, so we tested 4 different cartridges. These are cartridges that in modern rifles, mostly semi-automatic rifles that people use commonly for target shooting, AR-15s, AK-47s, M14s, and 14 different types of bullets, which I'll explain now. These are combinations of the bullet materials, lead, copper, and steel, whether it's in the core or in the jacket. So the most common kind of bullet for hunting or for target practice is a lead core copper jacketed bullet. Shown here, there's 2 different varieties, but there's lots of different varieties, and they have different thicknesses of copper, different amounts of lead, and all that. Another kind of bullet is composed of steel, and the steel can be found in both the jacket and in the core. On the left is a steel core with a steel jacket. It's got a large steel penetrator in that bullet. These are Army surplus, military surplus, but it also has a steel jacket, a very thick steel jacket. On the right is a small steel penetrator, but with a copper jacket and lead. We also tested lead core and just steel jacketed bullets like the one on the left, and also solid copper. Solid copper, they are non-toxic, and they're recommended for hunting. They're mandated for hunting in California only. So this is a high-speed video of a bullet impacting our steel plate. And what you'll notice there is immediately you see an impact flash. You'll see that bright amount of ejecta after the bullet impacts. And then the flash kind of fades, and what you're seeing now are glowing particles. You see all these glittering particles. Well, they're glittering because they're hot and they're glowing, and they're being deflected downward into that peat. So let me describe this really quickly. The impact flash is very hard to measure, but it's probably not hot. The impact flash is probably caused by mechanoluminescence, it's called. It's basically just light emitting from ions, excited molecules. And you can see the same exact thing by peeling Scotch tape in the dark. Right where the stickum on the Scotch tape is peeling back from the tape roll, you'll see light. And so it's obviously not hot. It's a luminescence. It's not hot. This happens too quickly. It's in less than a thousandth of a second. It's too fast for combustion to take place. So the second part of this image you can see in the bottom right are all of these glowing fragments. Those are actually hot, and they're not burning, but they're glowing bright enough to see in the daylight. So what happens is when these fragments land in the peat is they make a contact ignition with this dry material. And you can see here a strip of steel jacket, or steel core in this case, lying on top of the peat, and it starts a smoldering ignition. Okay, here's just another. Sometimes these fragments bury themselves in the peat, and then they begin a spot ignition underneath. And so we would count the number, and take a look after every shot, every 5 shots, how many ignitions did we have? And we also would sort through the peat and extract all of these little fragments. And so these fragments are very small. They're the size of an oatmeal flake, for example, most of them. So very, very small. It doesn't have to be large in order to start a fire, even though larger ones are more likely to cause an ignition. And so here are all these little tiny fragments that caused ignitions. So when we do our statistical analysis of all these different factors, the bullet material, the construction of the bullet, matters a lot. Okay, what you're seeing here is a graph showing the probability of seeing an ignition in our tests on the y-axis. So it goes up to 1.0 at the highest. It's 100% chance of seeing an ignition all the way to 0. And then on the x-axis is the impact angle. Like I said, we could change the angle of the deflector plate to change the sizes of the fragments. So when the deflector plate was very, very shallow, we ended up getting bigger fragments, and you get more likelihood for ignition. But notice here that the top line, this is the likelihood of having a ignition, is greatest for solid copper projectiles. I'll show you why in a minute. But these solid copper hunting bullets caused very reliable ignitions. It was very interesting, very surprising. The second most common kind of bullet for igniting fires was steel core and steel jacket. The more steel you have in the material, aside from solid copper, the more likely it was to cause ignition. The next line down, the third line from the top, blue line, is lead core and a steel jacket. And finally, and then going down, steel core and copper jacket. And the lowest chances of causing a fire with these are the standard hunting bullets, lead core and copper jacket. Okay, and so one reason for having the steel and the solid copper cause more ignitions is because the bullet fragments are larger. These are tougher materials, and they don't fragment as much intentionally for the solid copper. That's what makes them good hunting bullets, is they do not tear apart upon hitting a soft target. But so we had we filled, instead of peat in the collector box, we put water in there. And so we collected all the fragments. And you can see in the lower right-hand corner there, that's the solid copper. Look at the size of the fragments compared to, say, a lead core copper jacket, which is the lower left, much smaller fragments. So the bigger the fragments, the more likely it is to start a fire. There's more energy content in the fragment. So what are the temperatures of these fragments? Well, we used a thermal camera, and we also used a direct measurement using temperature-sensitive paints. A thermal camera is kind of difficult to do this without getting the camera destroyed by bullet fragments flying around, but we were able to capture images or video of the bullet fragments bouncing around, and we analyzed the maximum temperature in each frame. And you can see 3 different shots here, and over time, and the temperature spikes when the bullet smacks the deflector plate, and the fragments come to rest on the bottom of the collection box, and you can see the temperature goes up to almost 800 degrees C on that first shot. After that, it's not quite 600. But this is not a reliable way of estimating temperature, because we don't know the emissivity of the bullet fragments themselves. That is, what fraction of radiation comes off of it compared to absorbed. So we did a direct measurement, basically attached to that deflector plate, this birdhouse attachment, all made of steel, but basically the fragments are trapped inside it, are able to bounce around and then be funneled down to where they sit on a plate. And the plate is coated with thermally sensitive paint. And if it discolors the paint, then you know that the temperature was at least that high. And so here's another image showing a bunch of pictures of a plate coated with paint that was sensitive at 800 Celsius, which is 1400 degrees Fahrenheit. That's pretty darn hot. And there was discoloration on the plate from these fragments, meaning that some of these fragments were at least 800 degrees. So here's a summary of the findings. Bullet impacts are most likely on resistant targets, that is a rock or a steel plate. If you're shooting into dirt, it's not really a big problem. The bullet needs to stop instantly and fragment. That's what converts the kinetic energy into thermal energy. These fragment temperatures reached at least 800 Celsius. We don't really know. It's pretty darn hard to measure, but they're darn hot, plenty hot enough to start a fire. The bullet fragments were larger for steel and for copper solids. For lead core and copper jacketed bullets, they were very small and much less likely to start a fire. You need very dry organic material, so it has to be hot and dry. Sunny certainly helps. Low relative humidity. Probably the fuel moisture has to be between 5 and 9%, something like that. The only kind of ignitions we saw were smoldering ignitions, so they may take a while before you detect them. Someone shooting out in the wildlands may start fires, may start these smoldering ignitions that aren't detectable for maybe tens of minutes or even hours. But other times, if it's windy, it may ventilate the smoldering ignition into a flaming ignition fairly quickly. It just depends. Now, because these fragments are cooling so quickly, within seconds they're too cool to start a fire. The ignitions are taking place very close to the target. They're not taking place, hundreds of yards away, very likely. Okay, let's talk about the last study, the exploding targets. We published this in 2019. What are exploding targets? Well, they're recreational targets. They're made for just shooting, and it'll make a reactive a reaction, with both the visible reaction and audible reaction when it explodes. There are many brands sold throughout the United States and Canada. The bullet impact initiates the explosion by creating sufficient pressure to ignite it. There are different combinations for different kinds of projectiles. There's a standard kind of formulation for high-powered rifle bullets, and a different formulation for, say, rimfire bullets, 22 long rifle. Sometimes these are called binary targets because there are 2 ingredients. One, the main ingredients in there, although there are variations, the main is ammonium nitrate and aluminum powder. So we know exploding targets can cause fires. That is not in question. That was not the point of the study, because you can just get on YouTube and you can see all of the people shooting and starting fires. But the questions are, how exactly are they started? What are the factors involved? Now, most of these targets are made of ammonium nitrate and aluminum powder. As I said, the more aluminum powder that you put in it, the more sensitive it is to ignition. But aluminum is also the fuel, and it burns at a very, very high temperature, more than 3,000 degrees Celsius. Burning metal burns at a very high temperature. This is an old explosive. This wasn't invented by any means for exploding targets. It's used widely around the world for terrorism and other kinds of explosion, mining, and other things. There are commercial products that you can buy. in any hardware store pretty much, and they're totally legal. They're illegal to transport after mixing, because after mixing they become an explosive, and so you're transporting an explosive. They're different sizes, from as small as a half pound all the way up to, and people build their own to 30 or 40 or 50 pounds, but commercially I think they're sold up to about 2 or 2.5 pounds. Okay, so what are our observations? When we started doing this, we just playing around with it just to understand what factors we're dealing with. What we could see is there's a lot of variability from one target to the next, and this variability was expressed in terms of the apparent power of the explosion. You could feel from where you were standing, and also the brightness of the explosion. You can see in this picture all these sparks that are kind of glowing in there, and that's burning aluminum. Burning aluminum is burning very, very hot. So you can imagine it doesn't take very many pieces of burning aluminum against, falling on something ignitable in order to ignite it. So this was the hypothesis we pursued, that basically that burning aluminum in the explosion is causing this ignition. And so one of the factors that we varied was the target preparation. We mixed some very thoroughly, and we mixed some very poorly, very partially mixed. You can see different pictures there. We mixed different proportions of aluminum, 1% all the way up to 10%. The most common commercial target made is called tannerite, and that contains a standard 1.6%. So we went lower than that and higher than that in terms of the concentration of aluminum. When we're out in the field, we took fuel moisture samples immediately at the time of shooting, just before that, so that we knew what the moisture content of the fuels were. We placed targets, some on pedestals and some directly on the ground. That proved to be a very, very important factor. We had high-speed videos. We have a mobile laboratory. We brought high-speed videos out to monitor in thermal bands as well as visible bands, but we also measured pressure. And I'm not going to talk too much about pressure here, but measuring the explosive power of something is easily done with pressure, the overpressure. That's what makes the explosion. And so these are pencil probes that we arrayed out, aimed at the target, and we would be able to get pretty good measures of pressure, and then the change in pressure as the wave, the explosion wave, moved away from the seat of the explosion. So here's our results. In 2014, we were messing around, not taking any data, but we got 4 ignitions out of 11 shots. In 2015, we shot under very cold and humid conditions. We got no ignitions out of 46. 2018, it was very dry and warm, moisture content of 3 to 9%. We got 22 ignitions, almost half out of 51 shots. 2019, 40 shots. There were a total of 9 ignitions, but 2 different days, different weather conditions. On the dry day, we got 7 out of 21, and on the wet day, we got 2 out of 19. So here's some video of these exploding targets. You can see the fireball as the explosion starts, and this was one of the tests that did start a fire. It's impossible from looking at these videos to tell which ones would start a fire and which would not. So you see all that flaming debris inside the fireball. Well, some of that is the fuel, some of that's the aluminum, some of that's the straw bales in this case. But in this case, we did have an ignition. The next one, just for example, we did not get an ignition, despite the fact that there's this giant ball of burning aluminum that goes scooting along on the ground off to the right-hand side. And so there's a lot of factors involved, a lot of variability. That's what makes this really tough to study. So this particular test did not give us any ignitions. So let me show you the results really quickly. On the left-hand side, on the y-axis, the y-axis is the probability of seeing ignition. On the x-axis is the percentage of aluminum in the mixture. And what we see is 2 main factors came out of our work. One is whether the target was placed on the fuel, on the straw mat itself. That increased the likelihood of ignition tremendously, compared to if it was placed on a steel pedestal above the fuel, above the straw. And the reason is the explosion was deflected upward if it's on a hard surface. Whereas if it's directly on the fuel, the explosion is able to kind of penetrate into the fuel itself and lift up a whole bunch of that loose material and train it into the fireball. But the aluminum percentage mattered a lot, as we thought. The more aluminum you have in the mixture, the more likely you are to have an ignition, because more of that stuff is burning at 3,000 degrees or more, and it comes in contact.
Warning, sir.
I'm sorry?
Just a quick 5-minute warning, sir.
Yep.
Thank you.
Anyway, the percentage of aluminum matters, and whether you place it on a hard surface. Now, I talked about pressure. I don't have time to present all of that stuff, but it was inconclusive. We could definitely show, as this chart shows, that you have half-pound targets on the left and the 1-pound target on the right, that higher pressures were produced by larger targets, which is exactly what you think. Higher explosive yield or energy yield for larger targets, and higher explosive yield when you had complete mixing. So the purple bars are higher than the green bars. But other than that, there was no relation between the pressure and the likelihood of starting a fire. So we know we could control the explosive yield by how we prepared the target, but we could not change whether or not, we couldn't prove there was a linkage between that and whether or not we start a fire. The jury's still out on that. So here's a summary. Typically, we see flaming ignition immediate. So let's compare that or contrast that with shooting caused ignitions. Most of those are causing a smoldering ignition. Here, because we have such high temperatures of this burning aluminum, we're seeing flaming ignitions almost immediately. Sometimes smoldering, but mostly flaming. Fuels must be dry. Again, that's the case with all of these kinds of ignition. So sunny, hot conditions, low humidity. More aluminum means more likely to get a fire. Target placed on the fuel surface is more likely to start the fire than if it's placed on a hard surface. There are possible effects of these other factors, such as mixing, whether the target is completely mixed or partially mixed, or where the bullet hits. We tried testing that, but could not prove a connection conclusively between bullet impact location and so if it hits on the edge versus the middle, whether or not that causes ignition. So that's the end of the talk. I'll be glad to entertain any questions. Thank you.
Yes, thank you, Mr. Finney. We do have one question that came in, and we understand that you're the science research, and you've done some phenomenal job of presenting your data to us. But a couple of us are curious, are you familiar with any prevention efforts that are being implemented to address these types of ignitions?
Well, I am. I'm not involved in them, but this year in Utah, there was a publicized effort by the governor and the governor's office there to implore people to avoid target shooting out in the wildlands, given the very dry conditions they were experiencing earlier in the year. And it seemed to work. It seemed that having people understand that their shooting activities can cause fires, and that kind of official request seemed to make some differences.
So much. And there was just one last question that popped up. If you have any pictures of what's left, the aftermath for the fire investigation, if it was tannerite, to determine tannerite. So just another little curiosity question popping in there for the last 1 minute that we have.
Yeah, and that's an important question. I didn't really address that, but we worked with ATF, Alcohol, Tobacco, and Firearms. They're explosive experts on the exploding target study, and it's something they were very interested in. There is information in the report, but often what you find is unreacting ammonium nitrate prills sitting on the ground near the explosion, the seat of the explosion. So the ammonium nitrate prills don't often react, and so some of them are expelled from that site. You'll also find small pieces of plastic or other debris from the container used. Sometimes people use duct tape or some other tape on it, and that's present as well. Most of the other stuff is evacuated from the actual blast seat quite a ways. But if you look for prills, the little white pellets, you'll often find those, no matter how well mixed it is.
All right. Great. Well, thank you so much for that fascinating presentation, Mr. Finney, and I hope you all the best with the rest of your day. Thanks so much.
Thank you
And
very
just a
much.
reminder to the rest of our participants to hop on over to the next session room, and we'll see you in just a few seconds, actually. Thank you.